Welcome to the deep dive. We're going to be jumping into group theory today.
Oh yeah, group theory.
Which, as you know, is this fascinating area of math that really explores the hidden symmetries that kind of underpin everything.
It really does.
Around us.
Yeah, it's like the secret code, almost like a universal decoder ring.
I like that.
Yeah.
A decoder ring. So instead of uncovering hidden messages, though, we're revealing the fundamental patterns and relationships that govern our world.
Yeah, exactly. And the story we're looking at today is about the McKay Conjecture, which has puzzled mathematicians for decades now.
And the McKay Conjecture, so this was put forward by John McKay back in the 70s.
That's right.
And suggests that you can understand the complexities of a large group just by studying a teeny tiny piece of it called a Sylow normalizer.
Yeah, imagine trying to understand like a massive corporation just by observing one tiny little department.
Whoa, whoa, whoa. That seems like a stretch.
It does.
How can a tiny part reveal the secrets of the whole?
That's the beauty of the McKay Conjecture.
Yeah.
It suggests that there are these hidden connections, these deep symmetries that link the small and the large.
Okay, I'm starting to see why this is groundbreaking, but before we go any further, could you remind us what a group is in this context?
Yeah, so think of a group like a club with specific rules about how members interact. And these rules determine how the group behaves as a whole. Take the symmetries of a square, for example.
Like how you can rotate a square 90 degrees and it still looks the same.
Exactly. Those rotations and flips in the do-nothing option form a group.
Oh, I see.
And these groups can be used to describe much more abstract symmetries, too, popping up in things like quantum mechanics and even cryptography.
So the McKay Conjecture focuses on finite groups, so groups with a limited number of elements.
That's right.
And claims that by looking at these Sylow normalizers, which are smaller subgroups within the larger group,
Right.
we can unlock information about the entire structure.
Think of like a big organization with lots of departments. A Sylow normalizer is like a special committee that oversees one specific department, but its decisions can actually affect the whole organization.
It's like finding this hidden lever that controls the whole machine, even though it looks like it's just connected to a small part.
Yeah.
But how did John McKay even stumble upon this mind-boggling connection?
Well, John McKay, he was just exploring the world of finite groups when he noticed something peculiar. The number of ways you can represent the elements of a group using matrices often seem to be the same for both the larger group and its Sylow normalizer.
So he saw this connection between a seemingly random quantity and this tiny subgroup. Talk about a light bulb moment.
It was a moment of mathematical intuition.
But unraveling this conjecture wasn't just a weekend project.
Oh, no.
This was a massive undertaking, right?
It was a huge effort spanning decades and involving tons of mathematicians all over the globe.
So it was like a giant collaborative puzzle with each mathematician contributing a piece.
Yeah, a perfect analogy.
And one of the most crucial breakthroughs came in 2004 when mathematicians figured out how to focus on a specific set of groups.
Right. They were able to narrow down the battlefield, so to speak.
So instead of conquering this vast, complex landscape, they found a shortcut?
Exactly. A more strategic path to the solution.
But I understand there was one particular class of groups that proved to be especially challenging.
Yeah, these are known as groups of Lie type. And they're really important because they're the building blocks of many other finite groups, but their representations are really hard to work with.
And this is where Britta, Späth and Marc Cabanes enter the picture.
Yes?
And they weren't just colleagues, they were partners in life as well.
Right. Their story is fascinating. Späth had been working on the McKay Conjecture since grad school, and she had a real knack for seeing patterns and intuiting solutions. Cabanes was initially hesitant, but eventually Späth's passion and the challenge of these Lie-type groups captivated him.
So their collaboration wasn't just about solving equations. It was a fusion of intellect and emotion.
Absolutely. A beautiful example of how those things drive scientific progress.
But even with their combined brilliance, it took them years of effort to crack this final category of Lie-type groups.
Imagine 6 years grappling with abstract mathematical concepts, working through complex calculations, and all while juggling family life.
It's a testament to their dedication.
It really is.
And in 2023, they finally announced to the world that they'd proven the McKay Conjecture for all finite groups.
Such an exciting moment for mathematics.
A victory decades in the making, but why should we, the non-mathematicians of the world, care about this seemingly abstract conjecture?
Well, the impact of this proof goes way beyond pure mathematics. It gives us a new lens to study groups, a shortcut to understanding complex systems.
It's like they've handed us a master key that unlocks a whole new world of possibilities.
Precisely, and this new understanding could revolutionize fields like cryptography, where group theory is crucial for securing our online communications.
So this isn't just about proving a theorem, it's about opening doors to new technologies and deeper insights.
That's the beauty of math. It often leads to unexpected applications.
I'm hooked, but now that they've proven the conjecture, does that mean the story's over?
Well, not quite. While Späth and Cabanes have shown that the McKay conjecture is true, there's still one big question mark.
Ooh, a cliffhanger. I love it. What's the catch?
We still don't know why the McKay conjecture works. What's the deeper reason for this connection between a group and its Sylow normalizer?
So we've solved the riddle, but we haven't grasped the underlying meaning.
A great way to put it, and this is what makes this area of math so captivating. It's a call to explore further.
So the journey continues, buckle up, listener, because we're about to venture even deeper into the world of group theory.
Deeper we go,
Welcome back to the Deep Dive.
where we're on this incredible journey through group theory.
And exploring the aftershocks of Späth and Cabanes proof.
It's really groundbreaking work.
It feels like they've opened this secret door in mathematics and revealed a whole new world that we're just beginning to peek into.
And as we explore, we're realizing that the McKay conjecture is only one piece of a much larger puzzle.
You're saying there's more to discover, more secrets waiting to be uncovered.
Absolutely. The proof itself is just the beginning. It doesn't explain why the conjecture works. There's still this fundamental mystery about what truly connects a group to its Sylow normalizer.
It's like we've found a hidden passage, but we don't know where it leads or what we might find.
Exactly. That's what makes mathematical exploration so exciting.
So where do we go from here? What are the hot topics?
One of the most exciting areas is something called moonshine.
Moonshine, like the light from the moon.
Not quite in mathematics. Moonshine refers to these unexpected and often baffling connections between seemingly unrelated areas.
Like hidden bridges between different mathematical worlds.
Exactly, and it turns out that John McKay, the mathematician behind the McKay conjecture, was also a key figure in one of the most famous examples of moonshine.
No way.
Yeah, back in the 70s, mathematicians were grappling with this truly gigantic group called the monster group.
Just how monstrous are we talking?
Well, it has over 800 trillion elements.
Bro.
That's more than all the atoms in a billion Earths.
That definitely sounds monstrous.
And at the same time, mathematicians were studying this completely different thing, a special function called the J function, which comes from number theory.
So we've got this monstrous group and a totally unrelated function. How do those connect?
That's the question, isn't it?
Yeah.
And this is where John McKay's knack for patterns comes in again. He noticed that the first few coefficients in the expansion of the J function were remarkably close to the dimensions of certain representations of the monster group.
You're kidding me. Numbers from this abstract function were showing up in the dimensions of this monster group's representation.
It seemed like an incredible coincidence.
So there must be some deeper reason these two things are linked.
You're right. Mathematicians eventually proved that the connection between the monster group and the J function is not a coincidence.
Yeah.
There's a profound underlying structure connecting them.
So monstrous moonshine isn't just a catchy name, it's a clue to a deeper mathematical truth.
Precisely. And what's even more amazing is that monstrous moonshine hints at connections between group theory, number theory, and even string theory.
Wait, string theory, the theory in physics that tries to unify all the fundamental forces of the universe.
That's the one. It shows just how interconnected mathematics is.
So the McKay conjecture might not just be a mathematical curiosity, it could be a key to understanding the universe.
It's definitely a possibility, and that's what makes this research so exciting.
We're really pushing the boundaries here.
We're exploring the frontiers of mathematics, venturing into uncharted territory where every new discovery could change how we understand the world.
It's a grand adventure.
And who knows what we'll find along the way?
I can't wait to find out. We'll be back soon to wrap up our deep dive into group theory, the McKay conjecture, and the mysteries of monstrous moonshine. Welcome back to the deep dive. It feels like we've been on this incredible expedition through the world of group theory.
We've covered a lot of ground, from the basic idea of groups to that incredible proof of the McKay conjecture.
And of course, that fascinating detour into monstrous moonshine.
Yeah, it's been quite the journey. But as we wrap up, I think it's worth taking a moment to reflect on what we've learned.
So what are the big takeaways here? What should our listeners be thinking about?
Well, I think the first thing is just to appreciate the beauty and power of group theory.
Yeah, it's amazing how this abstract area of math can reveal these hidden connections in so many different places.
Exactly, from the structure of crystals to the fundamental forces of the universe groups, give us a way to understand patterns and relationships.
In the McKay conjecture itself, even though it sounds complicated, is really a simple idea at its core.
The idea that we can sometimes understand a huge, complex system by looking at just a tiny piece of it.
Like holding a grain of sand and seeing the entire beach reflected in it.
That's a great analogy.
Yeah.
And now that it's been proven, mathematicians have this powerful new tool to explore the world of groups.
It's like they've got a new set of glasses that lets them see things more clearly.
And this new understanding could lead to breakthroughs in other fields too, like cryptography physics, even computer science.
So it's not just about solving a math problem, it's about expanding our knowledge and opening up new possibilities.
Exactly. But I think the most important takeaway is that this is just the beginning.
You're saying there's still more to discover. The adventure continues.
Oh, absolutely. We still don't fully understand why the McKay conjecture works. What's the underlying connection between a group and its Sylow normalizer?
It's like we found the secret door, but we don't have the key to open it.
And that sense of mystery is what makes this area of math so exciting. There's so much more to explore.
So how can our listeners keep this exploration going?
Well, they could dive deeper into monstrous moonshine or learn more about how finite groups are classified.
There are tons of resources out there for anyone who wants to learn more.
And who knows, maybe one of our listeners will be the one to make the next big discovery.
That's the beauty of it all. The world of mathematics is open to anyone with the curiosity to explore it.
So keep asking those questions, keep searching for those connections, and never lose that sense of wonder.
Well said. Thanks for joining us on this deep dive into the fascinating world of group theory and the McKay conjecture.
It's been a pleasure. Until next time, keep exploring.